Hey guys, we're gonna go through a brief introduction on Friedel alkylation reaction, which is gonna be the the experiment next week we're about to do. It's gonna be an multi-outcome experiment. It's also the second experiment this semester we're gonna do that do not have a candidate bank to choose from. Again, this time you're gonna be using your spectral analysis skills and glean all the information you can get to identify the unknown alcohol. Okay. Alright, so firstly, let's talk about Friedel alkylation reaction. Firstly, it's an example reaction of EAS reaction, right? Electrophilic aromatic substitution, which is the full name of EAS. Then let's talk about the roles of reagent. The nucleophile of this reaction will be the electron-rich benzene ring, right? It can be, or it's normally an activated benzene ring. The electrophile in this case will be carbocation. You can create the carbocation using two catalysts. You can use either a Lewis acid like aluminum chloride, or you may use an acid to protonate and create the carbocation as an electrophile, and we're going to go through the detailed mechanism in a little bit. The catalyst is going to be either aluminum chloride or acid. We're going to choose acid as a catalyst for this reaction, for this experiment. Since we're using acid as the catalyst, the first step will be protonation of the tertiary alcohol. The second step will be kicking off water and create the carbocation intermediate. And then, since we already produced an electrophile, we're going to use a benzene ring as a nucleophile to do the attack, and then eliminate proton to restore the aromaticity of the benzene ring, which give us the final product. This is different. This is going to be different from the experiment we're about to do next week, right? The experiment we're about to do use 1,4-dimethoxybenzene as the nucleophile, and it's going to produce a dialkylated product. So 4 positions of the benzene ring is going to be substituted. In the experiment next week, you're going to be predicting, or you're going to be deducing the unknown tertiary alcohol, as well as predicting the substitution position on the benzene ring, right? The alkylation position. So if that's the case, then you will need to know you will need to know 2 things. Firstly, how the substituent will influence the EAS reaction. If your benzene ring have a substitution which is the electron donating group, it's going to tend to donate electron to stabilize the intermediate being formed on the left, right? And this will activate the ring and make the ring more prone to go through electrophilic aromatic substitution reactions. However, if your benzene ring are connected to an electron withdrawing group, then that's gonna destabilize the intermediate because it's gonna be absorbing or withdrawing electrons away from the aromatic intermediate. This tends to deactivate the ring and make it less likely to go through EAS reaction or Friedel alkylation reaction. The methoxy substituent is going to be a very electron-rich, electron-donating group, right? So that's going to tend to stabilize the intermediate and activate the ring. The next thing you will need to know is going to be the directing effect of the substituent. Some of the substituents are strongly activating and also para-directing, and some are deactivating and meta-directing. So you will need to figure out the directing effect of methoxy substituent based on this paragraph or this table, and then predict what's going to be the final product being synthesized, right? Spectral analysis can also give you some hint or some data for prediction. You also have the melting point range you can compare with. So I have strong confidence that you can successfully deduce the structure. But just FYI, if in the future you see EAS reactions, you see Friedel-Crafts alkylation reactions, you may come back to this table for future references, okay? And if your starting nucleophile, starting benzene ring, contain groups such as NH2, CF3, those strongly deactivating groups, then the reaction is very less likely to occur towards EAS reaction or towards Friedel-Crafts alkylation direction, because it's just gonna make the ring very deactivated and very reluctant to react. Okay, so be careful when in the future you saw a reaction that contains all the conditions required for EAS reaction. Think about the substituent. Is that activating or deactivating? Is that para-directing or is that meta-directing? And then figure out what's going to be your product, or the reaction is not going to happen, which is also possible. Okay. This is the other mechanism that we are not going to use, but also can occur or can be used for Friedel-Crafts alkylation reaction using aluminum chloride as a catalyst. So I'm not going to go through the details, but if you want to come back and refer to this, you may.